the last section, we were trying to find the absolute maximums and minimums of a function of two variables over a region of the plane. But we had a slight issue where we didn't know how to handle the boundary. The maximums and minimums could be on the boundary, and they wouldn't show up as critical points of the function. So here we are going to construct a technique for doing that, for dealing with boundaries, that will also even extend to talking about the boundaries of regions in three-dimensional space. Say, take the surface on some blob in three-dimensional space, and we can theoretically take a function of three variables and maximize it over that surface. Let's start with the two-dimensional case because the pictures will make it a little easier to see what's going on as we construct that technique. Let's say we start with our function of two variables, and just for illustration, let's go ahead and actually pick a function. I'm going to go ahead and pick y squared minus x squared, and we're going to have a boundary given by some curve. Now, there's a couple of ways we could give a boundary as a curve, but we're going to give it by an implicit equation. Some equation like g of xy is equal to some constant k. So we'll be just denoting our curves like that. In this particular case, I'm going to choose a circle. The equation x squared plus y squared is equal to 4. A curve like this, or when we move to 3 dimensions, a surface like that, just some equation that is limiting what values we're even looking at in the function. This is what we're going to call a constraint. And we'll say that we are maximizing or minimizing a function subject to some constraint. And so really what we're looking for is the largest and smallest values of y squared minus x squared among all points x and y that satisfy the equation x squared plus y squared equals 4. Let's go ahead and plot those. So we could go ahead and put in our function. Y squared minus x squared. We get this surface here. If you remember what this is called, this is a hyperbolic paraboloid. And I'm just going to make that lighter again. I feel like that shows up better, at least when it's not trying to select it and making it really dark. And apparently it doesn't want me to deselect it either. Okay. Yeah, we need the curve, which hopefully will show up as a cylinder actually, because that'll make it a little easier to see what's kind of going on here. And let's make this a different color. Let's make that. I apparently selected the wrong thing. Oh well. I meant to change the color of the cylinder. I changed the color of this of the hyperbolic paraboloid, but whatever. I just want them to be different colors. The point here is that there's a curve. There's a curve of intersection here, and those are the points that satisfy the constraint because they are on the cylinder x squared plus y squared equals 4, but they are values of our function. And so we actually end up with a curve in three-dimensional space, and we want to see how we could figure out where the highest and lowest points are. Now, in this particular case, we can actually see where those are going to be. You can tell that the highest points on those curves are the ones along the y-axis here, and the lowest points are along the x-axis. So you might be able to guess what they are in this particular case, but that's not a technique that will always guarantee that you can find it. And if you're just slightly off, you're not going to be able to figure that out just from graphing it. So we need a more robust technique than just looking at a graph. Now this picture doesn't, it shows us a lot about what's going on, but it doesn't really give us the clue that we need to actually construct our technique. So what we're going to actually do is we're going to look at this in 2 dimensions and look at level curves. So let me open up a. So I'll go ahead and get rid of that. So I'm going to go ahead and plot the circle. Hopefully, yeah, okay. Went ahead and put in my circle. That is the constraint. I want only points that are on this circle to be considered. And then I want to look at various level curves. Remember, a level curve, I'm looking at places where y squared minus x squared is equal to some constant, but I want to see this for multiple constants. So I'm going to take k's from negative 10 to 10. That will plot a sequence of curves. These are just the cross sections where we set of the surface that we looked at just a minute ago, where we set the z value equal to negative 10, negative 9, all the way up to 10. And we get a bunch of hyperbolas. Um, One issue with actually looking at this particular picture is that GeoGebra doesn't really label which ones are which hyperbolas are doing what. Just to kind of clarify things, the cross lines that go through the origin, that's the curve where k equals 0, where basically y squared minus x squared equals 0. That just means that x and y are plus or minus each other. The hyperbolas that are above or below the origin are actually increasing. So this is the curve where k equals 1, k equals 2, and so on and so forth. And the same going downwards, in fact. On the other sides, yeah, yeah. On the other sides, we are looking at numbers below 0. So this is k equals negative 1, k equals negative 2, and so on and so forth. And as we go out from the origin, we end up getting smaller values along the x-axis, but larger values along the y-axis. So it's kind of increasing from over here up to this point and then up to here. Now, what we can tell from this is that our curve, our circle here, it hits various level curves. So say at this point here, the value of the function at that point is 0 because on the k equals 0 level curve. Now, what is the largest level curve that it hits? What is the largest k value of a level curve that it hits? It would be, say, this one right here or this one down here. And both those are actually the k equals 4 level curve. You can just count them because I have them for all the integers. So 1, 2, 3, 4. So we can already see from here that not only is it actually hitting the highest level curve that it can at k equals 4, so that would be the highest value that can be on this circle for this function, but we also get a little bit more. We get the fact that the level curve of k equals 4 actually is tangent to the circle, both up here and down here. If we look at the other side and ask where does it hit the lowest point, it's hitting the level curve at k equals negative 4 over here, and it's tangent to it. And that's actually kind of the key point, that we end up tangent to our level curves. And that kind of makes sense because it kind of has to hit that lowest value and turn around and go back up. Or it has to hit that highest value and turn around and go back down. That's what ends up making them tangent to each other. Of course, that doesn't really work if we don't have nice differentiable functions, but as long as we do have differentiable functions, we have these nice smooth level curves, we're going to have to end up having them be tangent to our constraint curve. And that's really everything behind the technique that we're going to be looking at. This is going to work very similar for functions of 3 variables as well. let's look at a function of three variables, which GeoGebra won't be able to plot for us. But I'm going to go ahead and take the function x squared plus y squared minus z squared. You can't plot it because it would have to plot it in 4 dimensions. But at least I want it to be up there on the screen for you. I'm also going to take a constraint. This one will be easy enough for it to plot. X squared plus y squared plus z squared equals 4. So just kind of the same idea that we just had a moment ago. I'm also going to recolor that so it stands out from what we're going to be putting in here in a second. So we have a sphere. That we're looking at points on that sphere and asking what are the values of this function here. And notice the minus sign in front of the z squared, so they're not. This isn't just always going to equal 4. Now, because showing a bunch of level surfaces, it's going to be a little bit harder to do because if we draw them all, they're just going to be obstructing our view of each other. So what I'm going to do, like I did back when we talked about level surfaces before, I'm going to introduce a slider. Let's make this a wider range. And that will allow me to move between the level surfaces. Basically, I'll have a surface here, and it will change as I drag the slider. And so we're basically asking what happens when x squared plus y squared minus z squared is equal to this k value. And hopefully it will plot that. Okay, there we go. This is actually a hyperboloid of a, well, the one I have up here right now is of a single sheet, and depending on where I move my slider, I can turn that into a hyperboloid of two sheets. At the very cusp, when k equals 0, if it'll allow me to select it, we actually do get a cone. So various quadratic surfaces. We want to see what is the, let's start with the lowest point. What is the lowest point on the slider where this level surface hits our sphere? Because that will be the lowest value of the function on the sphere. Anything like at this negative 6.9, there's no intersection with the sphere, and so the function never takes on the value of negative 6.9 on the sphere at any point. So I'm just going to try to get it to where it just barely touches it. And it probably shouldn't be too surprising that it hits right at k equals negative 4. At y equals negative 4, we just barely touch. At the point, what is it, 0, 0, 2, the value of this function will be negative 4. But it is a point on the sphere because, well, 0, 0, 2 gives us actually 4 when we take their squares and add them up. Same thing with negative 4. The square kind of gets rid of that. So we actually end up with 2 different points where this function is minimized. But notice that we have kind of the same idea that we had in the two-dimensional case, where we actually do have because we have nice differentiable surfaces, that nice smooth surfaces here, we have them tangent to each other. And so that's a really nice condition that we're running into here. We have, as long as these are tangent, we actually can say that this works out very nicely. If we go for the other side, if we go out to say k equals 5.3, the sphere sits very nicely inside of there, but it never touches the surface, and so we don't have any values of the function. On the sphere, there's no values of the function that are 5.3. So we actually stop that. We'll go ahead and reduce this down to when we actually end up touching, and you might guess it is at k equals 4. Come on, let me select it. There we go. At k equals 4, it just barely touches the sphere on the sides. If I go any smaller than that, you'll start to actually see sphere poking out on the outside. But along this equator of the sphere, the values of this function are equal to 4. basically that sphere is where, or that the equator is where z equals 0, and so you have x squared plus y squared equals 4, and then that means in our function we have x squared plus y squared equals 4, and then no, the z squared is 0. So that is the highest value that we can get on the sphere for this function, is 4. Again, the sphere and our hyperboloid are actually tangent at those points. Now we do have it tangent along that entire circle, so we actually get a lot of points there. But we did end up getting that tangency that we were seeing in the other cases. And so that's what we're going to be looking for, even if we have to deal with an entire curve of tangent points. That is still what we're looking for. So how can we determine when we do have tangency? Well, here we're actually going to use the gradient. Recall that one property of the gradient is that if we have some implicit curve or surface, something that's of the form f of xy equals k, or f of xyz equals k, and we take the gradient of these functions, we get the gradient is actually a vector that points or normal to the curve or surface. Normal meaning here that it's perpendicular to the surface. And so if we have two surfaces or two curves that are perpendicular to each other, or that are tangent to each other, that they are, you could say they're parallel, but it also means that a vector that's perpendicular to both of them, or that is perpendicular to either one of them, has to be perpendicular to the other one as well. So, for instance, and I guess I never wrote this one down, so we were maximizing x squared plus y squared minus z squared, subject to the constraint of x squared plus y squared plus z squared equals 4. Usually we'll go ahead and name this. So a lot of times we'll write down the constraint without giving it a name, but we're really looking at it as a function of two variables equals k. So I'm going to say this over here is actually g of x, y, z. And I can look at the gradient of these two functions. So the gradient of f, remember the gradient, we take the derivatives with respect to x, y, and z and put those together as a vector. So derivative with respect to x is 2x. Derivative with respect to y is 2y. And derivative with respect to z is negative 2z. For g, instead, the gradient, so a lot of this works exactly the same way. We get 2x for the first one, 2y for the second one, and then just 2z for the third one. If we look at a particular point, so here I'm going to look at the point square root 2, 0. If we go ahead and actually plot that point, and apparently put it down here. Oh well. It is a point on both on the sphere and on our surface as long as we let k equal 4. So it's one of our maximum points. Gotta see where it is sitting in there. If we look at the vector, the gradient at that point. Now in this particular case, the z equals 0, so both these give the same result. That's not always going to happen in general, but we'll talk about what we can do to solve that problem. But when we plug that in, we get 2 square root 2, 2 square root 2, and 0 for both of those. If we plot that vector, so it's a vector that starts at a and then is modified by adding 2 square root 2, 2 square root 2, and 0. And it's a vector that just points directly out from both surfaces. It's perpendicular both of them. And being able to identify when that happens is going to actually solve the problem for us, basically. And again, I kind of wish it wasn't showing down here in this one, but whatever. So how do we identify when the constraints are when how can we identify when these gradients are parallel? Well, because might have to compensate for different magnitudes of that gradient, we'll have to introduce a scale factor. Traditionally, we choose a Greek lambda, and so we get this equation that we're trying to satisfy. We're looking for some point on our surface, on both of our surfaces, because it's going to have to be on both, but where the gradient the gradient of f at that point is equal to some scale factor lambda times the gradient of g at that point. If we can find an x naught, y naught, z naught that satisfies this equation for some value of lambda, it doesn't really matter what value of lambda. If it works for some value of lambda, then we're good. It's not necessarily going to be a maximum or minimum, but it's at least going to be kind of a critical point for our surfaces. Now, the book wrote this for 3 dimensions, but of course we can do it for 2 dimensions as well, if these were functions of 2 variables. In fact, the equation, if they just left out the x naught, y naught, z naught part and just said gradient of f equals lambda gradient g, then it'd be the same equation. But we can kind of summarize this in a result. We call this the method of Lagrange multipliers. And the lambda itself is the Lagrange multiplier that we're talking about. And we're basically saying if we're trying to find the maximum minimum values subject to some constraint, and we're assuming here that we do actually have those extreme values. We're not guaranteed those if our constraint isn't something that ends up with a bounded curve or bounded surface. So I showed you a circle and a sphere. Those are nice bounded closed regions, and so they're guaranteed to actually produce a maximum and minimum for a continuous function at least by our extreme value theorem. If our surface can go off to infinity in some way, that's not necessarily going to be true. But if it does have a maximum or minimum, if our function will have a maximum or minimum on that constraint, it will be at one of these points. So at the very least, we can identify whether, if there is one, we can identify where it is. And that's kind of our goal. We do have to note that our gradient of g is not going to be the zero vector on our surface. That has more to do with making sure it's a nice smooth surface. If the gradient of g can equal 0, we could end up with a sharp corner. And you should be aware by now that calculus doesn't really work well at those sharp corners. And so things can kind of break there. You might say that's kind of similar to when we were dealing with critical points just in general. We take places where the partial derivatives or the derivatives back in Calc 1 just doesn't exist. That would be the kind of similar thing here. Maybe you also look at where the gradient of g equals 0 and ask yourselves, and just kind of put those points into your list of points to check. But as long as we have those conditions, then any maximum or minimum points is going to have to satisfy the equation gradient of f is some multiple of the gradient of g. But you also need almost always, you're going to have to somehow include the constraint that you're using in doing that solving. And then we just do the same kind of thing that we did at the end of the last class, where we just plugged in our points that we get from this and see which one's the biggest, which one's the smallest. So let's actually try this out. It will make a little bit more sense when we do so. So here we have a function, just f of xy equals x times y. We have our constraint, 4x squared plus y squared equals 8. if we were going to plot that, that would be an ellipse. Of course, the first thing that we need to do is turn our constraint into a function. So we're going to make a function g of xy is equal to 4x squared plus y squared, and we want that function to always equal 8. That's going to be our curve. Even if it's an ellipse, we don't really need to necessarily know that, but we do need to actually set it as a function to actually use our technique. And then we'll go ahead and take the gradients, look at the gradient of f and the gradient of g. The gradient of f, we differentiate this with respect to x first, which leaves us with a y, and then with respect to y, leaves us with an x. If we differentiate 4x squared plus y squared with respect to x, we get 8x, and with respect to y, we get 2y. And so these are going to have to be equal to a multiple of each other. So we're going to have yx is equal to some lambda times 8x 2y. But usually what we'll do is just turn this into a set of equations. So here the first component, y, is equal to lambda times the first component over here of 8x. So I'm just going to write that down as y equals 8 lambda x. Then we do the same thing with the second component. This x is going to have to equal lambda times this second component of 2y. So we end up with the equation x equals 2 lambda y. Now, we have two equations here with three variables, x, y, and lambda. Usually we'll say that we can't solve that if we have too many variables. But if all we had were two equations, that would be kind of a problem. But we don't. We actually have a third equation. We have our constraint. We also have to throw in 4x squared plus y squared equals 8. Now we have three equations with three variables, and we could potentially solve this. Of course, this is kind of the trickiest part, because these are not linear equations. We're not guaranteed solutions. We're not guaranteed that it's easy to find solutions. But we just kind of have to play around with things and see what happens. I can't really give you a strategy guide for this part. We just kind of have to play around with it. But we can still use some of the same ideas that you might have used with linear equations, like try to eliminate a variable or stuff like that. Another thing that's frequently useful is to kind of break things up into various cases. We're going to see a little bit of that here. But let's try to eliminate one of our variables. I'm going to go ahead and take, and if you want to try this out for yourself before I go through it, you can do that. I'm just going to do the one that I found. May not be the best one. I don't really know, but this one worked. But what I'm going to do is I'm going to take these first two equations and I'm going to use them to get rid of the y value. Basically, I see that x is equal to 2 lambda y, but then y I can replace with 8 lambda x. Which I can go ahead and write as 16 lambda squared x. So x is always going to equal 16 lambda squared x. Now this leads to two possibilities. I would like to be able to divide out the x to have an equation that only deals with lambda, but x might possibly be 0. So I'm going to have two cases, which I'm just going to write out very explicitly just because this is the first time we're going through this. In later examples, I might not do this quite as verbosely. But in case 1, I'm going to say x equals 0. In which case, we're done with this equation because 0 equals 0. Nothing special about that. But what would that imply about the other ones? I can go ahead and plug that back into these equations and see what happens. Well, if I plug that into the first equation, we get something interesting. We have 8 lambda times 0, which is 0. Okay, that means that we'd be looking at the point at 0, 0. Is that a good point for us? Is that a possibility? Well, no, that the point 0, 0 does not satisfy our other equation. It is not a point on our ellipse. So this doesn't lead to any solutions. Because x equals 0 would force y to be equal to 0, but that's not a point that we can even use. It's not a solution to the set of equations. So we end up getting to basically say that x is not going to equal 0. In fact, that's something we might have been able to tell from the get-go, where we couldn't put 0 in here and get 0 for y. We also couldn't plug 0 in for y because we get 0 for x. So 0, 0 for either variable doesn't really work. If x is not equal to 0, now we can look at x equals 16 lambda squared x, and we can divide out x. So 16 lambda squared equals 1. Or we can go ahead and divide by 16, take the square roots. We end up getting lambda is plus or minus 1/4. Well, we're really more after the x values, or the x and y values. So let's actually go ahead and take this lambda and put it back into these equations. Let's actually look at this first one. We have y equals 8 times lambda, which is plus or minus 1/4, times x. Or in other words, if we simplify this, we get y is equal to plus or minus 2x. And that's a pretty good condition. I mean, it does actually, this is actually two different possible conditions, but once we have an equation just with the x and the y, we can use that with their constraint and not even have to worry about the lambda from this point forward. So we have what? We have, let's start with y. Y is equal to plus or minus 2x. We also have 4x squared plus y squared equals 8. I'm going to go ahead and replace the y with this plus or minus 2x. And then go ahead and kind of combine like terms. So this is 4x squared. This is another 4x squared. That's going to equal 8. Of course, we have a total of 8x squares over here, which we can go ahead and divide out the 8 and get that x squared equals 1. Or in other words, x equals plus or minus 1. If x equals plus or minus 1, y is going to have to be plus or minus 2 because we have to multiply by either a positive or negative 2. But keep in mind, because we have a plus or minus here and a plus or minus here, means that any possible combination of the signs is going to be another possibility. So we actually get 4 different points where we take both positive, both negative, or one is positive and one's negative, and we can switch those. But these are the only possibilities. We've eliminated any other possibility. We had one place where we kind of might have had a branching path and had to consider something else, but we already kind of dealt with that. We didn't get any solutions when we set x equal to 0. So these are the only possibilities, and I'm going to go ahead and make a table of those values. Oops. So we have one or both positive. I'll put down here both negative. Here I'll make one positive but two negative, and here one negative and two positive. Remember our function, I've forgotten what that is by now, but our function was originally xy, so we're just kind of multiplying these together. So 1 times 2 is 2, 1 times negative 2 is negative 2, negative 1 times 2 is negative 2, and negative 1 times negative 2 is a positive 2. So we end up with two maximum values at two different, well, they're not two different maximum values. It's the same maximum value of 2, but it occurs at two different points. Same thing with, we have a minimum value of -2 that occurs at 2 different points. And that's our solution. Depending on how we want to write that out, you might say a minimum of 2 occurs at point 1, 2, and -1, 2, or sorry, -1, -2, and then a minimum of -2 occurs at point 1, -2, and -1, 2. Let's try an example with 3 variables. So here, f of x, y, z is equal to x times y squared times z. And then we're subject to the constraint of a sphere. Most of the problems that the book gives you are going to have constraints that are like spheres, because we want that nice bounded region, or this nice bounded surface or curve. We don't want it to go off to infinity, and circles and spheres are very nice for that. Again, we need to identify what our constraint function is. A lot of times you can kind of not bother writing it down. Just kind of assume that this, whatever you have over here, is going to be your g value. But be careful that we have to have it equaling a constant. If there's, say, this was x squared plus y squared equals 4 minus z squared, you have to move the z squared over and have everything on this side. But hopefully that's easy enough to remember. Again, I'm going to take my gradients of these functions. So the gradient of f, differentiate with respect to x, leaves the y squared z. If we differentiate with respect to y, we get 2xy z. If we differentiate with respect to z, we get xy squared. Do the same thing with g of x. Well, we actually dealt with this exact same sphere before, so if you recall what that was, is 2x, 2y, 2z. Now, of course, the gradient of f is going to equal lambda times the gradient of g. I'm just going to immediately write that down as a system of equations. So I'm going to have y squared z is equal to 2 lambda x. So looking at the second one, we have 2xyz is equal to 2 lambda y. And then finally, xy squared is equal to 2 lambda z. Of course, we have a system of equations with 4 variables and 4 equations. We have to include that constraint as well. We have x squared plus y squared plus z squared is equal to 4. And we want to solve this system of equations with 4 equations and 4 variables. Again, it's not very straightforward, and you have to play around with it just until something works. Again, you might want to try it for yourself before you see how I do it. And if you find another way of doing it, that's great. Just be careful about like dividing by 0 and stuff like that. What I did is I took my first equation, this one here, and I multiplied it by x. So we end up having an extra x over here, and then we have an x squared here. I did a similar thing. I multiplied the second equation by y, but then I also divided by 2. That turns this y in the middle to a y squared. But now we don't have the 2 over here, so we have a lambda y. We actually have a y squared because I multiplied by by y. And then I did exactly the same thing with the third equation, where I multiplied by z. So I have xy squared z is equal to 2 lambda z squared. And now I have 3 equations where I have these 3 different values that are all equal to the same thing. So that means all 3 of those have to be equal to each other. We have 2 lambda x squared is equal to lambda y squared, and has to equal to 2 lambda z squared. That's a pretty nifty condition. Now, you might notice here that if we could divide out by lambda, we can simplify it. Everything has a factor of lambda in it. of course, that can only work if lambda is not 0. So we're going to have to break up into cases again. I'm going to leave off the lambda equals 0 case for now. I'm going to assume for the moment that lambda is not 0. And we'll have to deal with lambda equals 0 as another possibility later. Because this time it won't immediately lead to some contradiction that will lead to no solutions. So we actually do need to consider both these separately. But if lambda is not equal to 0, that means that 2x squared is equal to y squared is equal to 2z squared. And what that essentially means is that we can say that y squared is equal to 2x squared, and we can say that z squared is also equal to x squared. Why don't we go back to our constraint equation that involves x squared, y squared, and z squared? If we take that constraint, we have x squared, we replace y squared with 2x squared. We replace z squared with just x squared, and we want that to equal 4. Of course, here we have 4 copies of x squared, so actually x squared is going to have to equal 1, which means that x is going to have to equal plus or minus 1. Same thing with the y squared and the z squared. So z squared equals x squared means that x and z have the same value of 1, but with possibly different pluses and minuses. So we have z is plus or minus 1. Y is a little bit more complicated because we have to deal with the 2. But if x is plus or minus 1, then y squared equals 2. And so y is going to have to be plus or minus the square root of 2. But there's no real constraint here about which of these pluses and minuses correspond to other ones. In fact, if you try all the different possibilities in these first 3 equations, you'll see that any combination of these signs, it actually works. So we actually end up with 8 different points here. We end up with 8 different possibilities. We're going to later on put those into a chart like we did before, but just be aware that we have all these different points. One thing to note in this part, we assume that lambda is not equal to 0. We never actually found lambda, but because we're really more just concerned with x, y, and z, and we're using lambda as a tool to find the x, y, and z, we don't really need to find lambda if we can get away with it. It actually wouldn't be too hard to solve for it if you do care about it, but I'm satisfied that I have x, y, and z, and I'm just going to move on. What about the case when lambda equals 0? So we excluded that possibility before. Now we need to look at it anyways. If lambda equals 0, recall we have our equations here. That's going to change our first 3 equations. I'm just going to kind of write those down. That means that y squared z equals 0, 2xyz equals 0, or I could leave out the 2 now. We have x y squared equals 0. And of course, I guess we could go ahead and write down our constraint again, just to have it on this page. Now, one thing you could note, all 3 of these equations involve y. If y were equal to 0, that would be fine. It would satisfy those equations. So we could say y equals 0, and if we do that, that actually, if we look back at our constraint, that implies that x squared plus z squared equals 4. If we have any points x, y, or z where x squared plus z squared equals 4 and y equals 0, it's actually going to be a solution. It's going to force these to be true. So, in fact, we have an entire circle of points here, an entire circle of critical points, you might say. So we're going to have to include all of those points. On the other hand, if we didn't assume that y equals 0, what would that mean? So again, so we kind of broke up into cases of lambda equals 0 versus lambda not equal to 0, and then our lambda equals 0 case split up into two more cases of y equals 0 and y equals negative, y is not equal to 0. That's actually a pretty common thing to do in these sort of situations, in these sort of solving that you run into with Lagrange multipliers. But if y is not equal to 0, well, if y squared times z equals 0 and y is not 0, that means that z has to equal 0. Same thing here, x times y squared equals 0. If y is not 0, then x has to be 0. So this is going to lead to x and z both being 0. And if that's the case, then looking back at our constraint, we have that y squared is equal to 4, or that y equals plus or minus 2. So this gives us 2 points, 0 to 0, or 0, negative 2, 0. And we'll have to go ahead and put those into our table as well. So let's actually make our table. It's going to be a fairly big one, just because we had 8 points for our first case, we had an entire circle for our second case, and then we had 2 more points for our third case. I'm going to kind of cheat the format of this for the circle, I guess. But first I'm going to go ahead and put in our 8 points. So we're going to end up with 4 with a plus 1 and 4 with a minus 1 for our first points. Those will correspond to square root of 2, square root of 2, but then with a 1 or minus 1. Then negative square root 2, negative square root 2 with a 1 and minus 1. And same kind of thing down here. Now you don't necessarily have to write all of this out, but I want to make it very clear exactly what's happening here. I'm going to go ahead and put my 0, 2, 0 that we found, and the 0, negative 2, 0. Down here at the bottom, I'm going to put in this condition, this whole circle, which I can't really write out as x, y, and z because there's infinitely many points there. But it'll turn out we can handle that circle pretty easily in this particular case. Technically, in general, you might even have to do a new Lagrange multipliers problem for this constraint down here, or for this constraint. You basically set y equals 0 in here. You have a function in terms of x and z, and then you have the constraint x squared plus z squared equals 4. In this particular case, because our function, which I guess I'll remind you is x times y squared times z, when you put 0 in for y, it just makes 0 for that entire circle. So we're actually saved from having to do kind of a stacked problem like that. But in general, for more complicated problems, you might have to do something like that. In fact, you can kind of see that if x or z equals 0, then we get 0 there as well. So actually, we have zeros for those as well. Now about the other ones. Well, here, the fact that we have square roots of 2, well, we have a square. So all the y's here, no matter whether it's a positive square root 2 or a negative square root 2, they're always going to give us a 2. And it really just depends on whether x and z have the same sign. If they have the same sign, we're going to end up with a positive 2. If they have opposite signs, we're going to end up with a negative 2. So actually, we just end up with a collection of positive and negative 2's. Comparing our various values here, of course we have values above 0 and below 0, so all these zeros down here didn't really matter in the long run. But we can see that we actually have 4 different places where we have a maximum value of 2. So 1 square root 2, 1, 1 negative square root 2, 1, -1 square root 2 -1, and -1 negative square root 2 -2. Those all give you a maximum of 2. Then we have 4 different points that have a minimum of -2. I'm not going to list those ones, but you can see them from the table. Yeah, so that's the process. Of course, there's a lot of actual playing around that I can't really tell you exactly how to do, but at the very least, it's generally easier to do that with solving the system of equations than it is to try to do something different. And that's why we have this technique. I'm going to do another video where we're going to actually look at another way, well, not another way, a complication that you might arise when you're doing these problems. And I'm also going to go ahead and do an example where we return to what we talked about last section, where we're trying to maximize a function over a region, and actually both do the stuff that we were doing in the last section, and then use Lagrange multipliers for that boundary. But it is running long. I'm aware, but I'm going to make another video. Okay, so I'll see you there.